All right, everybody. I suppose we should get this show on the road here. Yeah, I've already talked to a couple people about the weather coming tonight. I'm also a little nervous about the weather. I don't live very far away, so I guess I might not be as worried as some of you are. But if you are uncomfortable and you want to get out of here because you're worried about getting home safe, do it. You don't need to ask me. That is far more important than listening to me yap about computers. You're not going to offend me, right? I understand completely. I may, depending on how things go, we may even cut class a little early to try and get people a head start before the storm gets here, so that you're all not driving home through a big. It's supposed to hail. I heard it's supposed to be lots of big hail. So I don't want people driving home in that. I don't want to drive home in that, and I only live 5 minutes away. So we'll see how it goes. I'll definitely check over the break and see what the weather forecast looks like, and we may adjust accordingly. But don't worry, do what you got to do. It's basically the thing there. You're not going to make me unhappy if you get up and leave in the middle of class. I completely understand. As far as class goes, though, as I'm sure you all are aware, we've got our presentations coming up next week. So every person has been signed up for one. There's only two on Monday, which means that I am going to fill the rest of the time. I haven't quite decided what I'm going to fill the rest of the time with yet. Actually, I'm kind of hoping, fingers crossed, the new top 500 list will be out, and I can talk to you about that. I've been refreshing that page every day, waiting for the new top 500 list to come out, and it's not out yet. I'm not quite sure when they plan to drop it, but we're definitely going to chat about it when they do, and kind of hoping they do it by Monday, because I would like to chat about it on Monday after our student presentations. But then, the other days are basically all student presentations until our first exam. So I just wanted to kind of give a couple of reminders, because I know that a lot of you are probably prepping your presentations as well as finishing up the first homework assignment, right? I wanted to remind you all that, a couple things actually. I do want to post your slides on the website because, as I believe I mentioned before, the presentations are fair game for the exam. So I want everybody to have the slides to use as a reference on the exam. I'm also asking you to submit 3 exam questions with your slides. If you could send them with your slides and all in one go, that would be perfect for me. That would be the most ideal way to do it. But I want to remind you all too, don't freak out or don't worry too much about the questions themselves. Hey, how's it going? If I need to tweak your question to make it a little bit more exam ready, a little exam friendly, I will. I'm just kind of looking for topic ideas from your exam questions, and I will make sure that they're exam ready for the actual exam coming up in a couple weeks. So you don't need to stress too much about the form. They can be any format that you want. A lot of people pick multiple choice, true false kinds of questions. I don't have a problem with that. Fill in the blank kinds of questions. If you want to make a bigger question that's a bit more complicated, go for it. I may or may not choose to actually use it on the exam. It kind of depends, but I'm in favor of anything that you are interested in talking about regarding your presentation on the exam. So please send me your slides and those 3 exam questions. It doesn't have to be before your presentation, but shortly thereafter, especially if you're presenting on the 29th, because there's just not a whole lot of time between the 29th and then. One other thing I want to chat with you about regarding the presentations, I've been thinking a lot about the structure of this class, and actually I think it's been going pretty well so far, although it's only been 2 weeks, and it feels to me like it's been a lot longer than that. I don't know how you all feel about it, but we've covered a lot of ground in a short period of time. One thing that I actually have kind of changed my mind about is the presentation feedback. I was originally going to make you all give feedback on the presentations. I'm worried about the homework assignments and the exams and the presentations themselves. I'm scrapping that. That's going to be scrapped. I'm not going to ask you to submit feedback on the presentations. I will be giving everyone feedback on the presentations. So you'll definitely get my feedback on the presentations. As far as the points that were there for the feedback, I think it was 10% of your final grade. So that's probably just going to be a freebie. You're welcome. not my, if I had planned a little better, maybe I would have written the syllabus not to have those in the first place. I think what happened is I was trying to stick too close to the 15-week schedule, but when you cram it into the 8-week schedule, it's just too much. I feel like it's too much for you all. It's also too much for me. I have to grade all this stuff. So trying to pull a release valve here. The feedback portion is no more. So you don't have to worry about that. But once again, the presentations will be on the exam, so I feel like that enough is a good reason to come and pay attention and take notes on the student presentations. Yeah, I'm trying to think of what else, logistics or structural I need to mention. Does anybody have any questions about the present? Oh, actually, I forgot one more thing. Some of you still not picked a paper yet for your presentations, and that's okay. I understand. But if I don't have your paper, probably by the end of the week, I'm going to start poking you. So definitely take a look sometime between now and the weekend. If I don't hear from you, I'm going to start grading the homeworks actually probably this weekend. And while I'm doing that, I'm probably going to check and see who hasn't submitted a paper to me yet for the presentation and send you a little poke if you haven't. So just kind of keep that in mind. And if you have a chance in the next couple days, I know you have the homework assignment due. But if you have a chance in the next couple days to pick out a paper from the list and let me know what you're going to present on so I can get that on the calendar, I really appreciate it. I think that does it as far as logistics goes. Does anybody have any questions about the upcoming presentations or the homework assignment or anything else that I was just talking about before we hop into today's topic? Seems like people feel pretty good. For those who walked in a little bit late, I just want to repeat that I am aware of the weather, so it looks like that storm might be rolling in right around the end of class, so we may adjust accordingly. I'll probably check the weather on the break and see if we need to adjust, but hopefully we'll be able to get through everything today. I'd like to. All right. Today we're going to be talking about a tool. So this is actually a very important tool called TAU. Stands for well, you can see right there on the slide, stands for Tuning and Analysis Utilities, and this is, excuse me, this is kind of the grand finale of the tools that I'm going to be introducing in this class. This is the professional grade one, right? This is the one that, you know, if you're looking at the actual supercomputers on the top 500 list, this is the tool that they're using to analyze the performance of their code and make adjustments. So this is the real deal. Not to say that gprof and perf aren't useful tools. If you're, you know, just doing little tiny things, gprof is great. You don't need a full-fledged, you know, professional tool to analyze simple little programs if that's what you're interested in. And perf has its own advantages in terms of its simplicity compared to TAU, which you'll see as I show you some of the things that it can do here in just a minute. But if you're really digging in, you want to know all the ins and outs of the performance of your code, this is the tool to use. It's kind of the gold standard in the high-performance computing world right now. So I'm not going to be able to cover every single thing that TAU can do. I'm going to try and hit the high points. I've linked the tutorial / documentation to TAU on the Canvas page. So as you're working on not the current homework assignment, but the next homework assignment, that's probably going to be a very useful reference for you. I've also linked some YouTube videos here, which are actually kind of the basis for these slides to some degree, although as we get closer to the end, it'll be more, anyway, it'll be more about stuff for this class, not so much about TAU. But yeah, let's go ahead and dive right on in. The nice thing about TAU is that it's trying to do everything. So it's trying to support every language. It's trying to support basically any program that you might consider running in a high-performance environment. So you can see that the ones we care about are on there, C and C++. To be perfectly honest with you, those are probably the languages that are going to be running the most high-performance code if we're talking about supercomputers. But people are also interested in the performance of other kinds of codes as well, not just supercomputers. So it can handle Java, Python, and bunches and bunches and bunches of other languages as well. One of the things that it's really well known for is the graphical displays. So it has the ability to display data in all kinds of shapes and forms, which you'll actually get to see. So this part of, actually, maybe I should have started with this. This part is actually only going to take us up to our usual break time, and then after break, I'm hoping that you all get a chance to get your hands on Tau and try it out. That's the goal for the end of, for like the last hour of class today, is to show you how to set it up and try a few test programs and make sure that you actually know how to run it properly. So, and so that graphical display is kind of what it's known for. I'll show you some examples of that in a little bit. It supports all kinds of programming paradigms, so you can see the ones that we care about up there. P-threads is the target for assignment 2, and then OpenMP is the target for assignment 3, and then MPI is going to be the target for assignment 4. It also does GPU stuff, which is increasingly important in the world of high-performance computing, so important for it to do those languages as well. And as I kind of mentioned, right, they're trying to do it all. They're trying to be the Swiss Army knife of profiling tools. They're trying to put all the other profiling tools out of business, basically. And I would argue they've pretty much succeeded in that. It's a very robust tool that can do so many different kinds of things. As far as how it works, there's two primary types of observations. Direct observations and indirect observations. That slide actually probably should have been cut because it was so short. Just as a little reminder for your student presentations, that was a mistake on my part. If you have a slide, you should talk about it for at least a minute. That one was not. That one should have been cut when I was prepping for today. But let's talk about direct performance observation. The way that this works is that Tau is going to instrument your code. So it's going to stick what they call probes into the code to measure whatever it is that you care about measuring. For a lot of cases, that's probably just time, right? But there's lots of other things that Tau can measure as well. You may remember that giant list of stuff that perf shows you. I'm certain that Tau can do most, if not all, of those same kinds of measurements of your code, including things like caching and, some of the pipeline stuff like branch prediction kinds of things. That's all available through Tau as well. And what's interesting about the way that Tau does this, you can either do direct performance observation in a few different ways. You can actually have it do it directly on the source. You can have it do it during compile time, which is probably the way that we're primarily going to be using it, is at compile time. But I'll also talk about it can actually take an existing binary that's already been compiled and rewrite it, which is very interesting and perhaps a little problematic in some ways because, I mean, a lot of, depending on how optimized that binary already is, it can be hard to, track certain pieces of information. If I've inlined all my functions, for example, that's going to be very hard for Tau to give me information on those things. So it's kind of cool that it can do it. In practice, I've personally had kind of mixed results with the binary one, which is why I'm going to stick more with the compiler level rules. And so the nice thing about direct performance observation is that it gives us the most detailed information, because Tau, what it does, so if we're interested in function performance, it's going to insert a probe at the beginning of that function, it's going to insert a probe at the end of that function. And so every time that function is called, it's literally recording I entered at time x and I left at time y. So we're going to get the most accurate, most up-to-date, detailed information that we possibly can. The downsides, think about if your function is short and it's only got a couple lines. Well, now I've inserted those two probes. That may end up being now the bulk of the work. That may now end up being more than the actual, code itself within that function. So for certain kinds of, edge cases, Tau can be a little heavy-handed. So it's important to understand that. It does take a little bit more compiler time as well. And it can be a little bit finicky because Tau is actually sort of augmenting the compiler, I guess, would be the best way to consider it. It still uses GCC under the hood, but then it's doing a whole bunch of other stuff on top of it. And sometimes that can be kind of opaque, what it's actually doing to the code. So it's a little bit unclear exactly what it's doing unless you want to dig real deep into the compiler output, which, let's be honest, nobody really wants to do that. It can be a little tricky to understand exactly what's going on. Indirect observation, on the other hand, is similar to how gproc handles performance measuring. So it's just going to periodically pause the execution of the program and say, hey, where are you at? What are you doing? And so it's sampling. It's just going to sample periodically the program. You can also have it be triggered by certain events. So if I miss the cache, right, then I want you to see where that happens. Take a sample at that point in time, see where we're at. Excuse me, and things like that. It's gonna, yeah. So the downside, or the upsides, I guess, of let's start with the pros. The upsides of this indirect performance observation, we don't have to modify the source code at all. So this is all done at runtime. There's no actual modification to the code or the compiled output of the code. But the downside is actually some of the downsides of gproc. That sample rate then becomes such a huge factor. If I'm sampling far apart, I'm going to lose, information in between those samples. If there's a really short function that is shorter than my sample time, I might miss entire executions of that function, right? Excuse me. The opposite has negative effects as well. If my sample time is really short, I may get more accurate information about my path through the program and what functions I'm calling, but at the cost of a lot more overhead for that higher sampling rate. So, as with all things computer science, it's about trade-offs. We've got two types of measurements that Tau can provide for us. The first is profiling. We're going to see this. This will be a lot more clear once I show you some pictures of what Tau looks like and the kinds of information that it supplies. But much like gproc can do, it shows us the time spent in each of our function calls, the number of times that something was called. But we can also do tracing and show a call graph, essentially. Although it doesn't necessarily have to be a call graph, it can also be any events and show the order that those events occurred in, because that could also have a huge effect on your program. If you see a whole bunch of cache hits in part of your program, that's an indication that or misses rather, not hits. Hits are a good thing. Misses are a bad thing. If you see a whole bunch of cache misses in part of your program, that's going to be a clear flag that, hey, you got to go check that out. See what you can do about that code. So here's the flat profile. Here's an example of what Tau looks like. It's not the most beautiful program in the world, but I don't think they care. That's not really what they're going for. This image, by the way, as well as almost all the images, are ripped directly from the tutorial. I didn't capture these myself. Tau is maintained by the Computer Science Department at the University of Oregon, so that's where the tutorial and all the documentation lives. But yeah, you can see on this flat profile, it's really a list of every single function that has been called. We can actually tell from this example that this is an MPI program that has been executed here. We're not going to get to MPI for a few more weeks until after the first exam. But eventually we'll get there, and you can see that, okay, up at the top, the MPI receive took the longest time out of everything, 13 some seconds, and MPI init took the second longest time, and so on and so forth. We see send is farther down the list, as well as some other MPI values down here as well. But it doesn't just have to be time. It can be how many instructions were executed, how many cache hits, misses, etc. I'll show you all that stuff once we actually get to take this thing for a spin and try it out. Here's the call path profile. So it's a nice visual representation of which functions get called and by whom. gproc also showed us this, right? But compared to that text-based output that can be kind of hard to understand, this is a lot more visual. I think think, a lot more direct in terms of conveying that information. We can see very clearly that the main method is going to call, or the main function is going to call F1 and F5, and then F1 calls F4 and F2, and F4 also calls F2, and so on and so forth. So, nice, handy visual representation of that call path profile. And then here is kind of one of the fancier things that Tau can do for you. 3D visualization. So it can actually generate plots of your execution data. And so on this particular, it's hard to read on the slide because the text is so small. But on this particular axis, we see we've got threads. Over here, we've got functions. So which threads we're spending the most time in which function. And then on the z-axis, the vertical axis, we have seconds. And you can see that this function in particular appears to be a huge time sink. It's got a big giant ridge there. That's actually the MPI receive call, I think probably from the same flat profile we saw a few slides back. Right? But with this view, we can actually see how much time each individual thread spent in that particular function. So we can get a thread-by-thread breakdown of how much time was spent in each particular function. Again, if you're trying to narrow down where the bottlenecks are in your code, this is invaluable information, right? So lots of cool stuff you can do. Over on the right-hand side, you can see there's lots of different ways that you can tweak these visualizations as well. Some people in the past have even used some of these visualizations directly in their reports to illustrate, the data that they collected, and I think that's wonderful. The big problem with doing that, though, is this one in particular is not very readable. So making sure the axes are readable can be a little tricky. Tweaking the values, making it look presentation ready, is going to take a little bit of extra time if you want to go that route. All right. This particular view is going to show us stats about every single thread. We can actually select each individual thread and then see stats about each individual thread, including so these are going to be all of the method calls again of that thread with inclusive and exclusive time listed here, as well as how many times these were called and how many more calls are made from that particular one. I'm going to talk about inclusive versus exclusive time, I think, on the very next slide, although it's a similar concept to one that we've actually already kind of discussed. Gprof called this, oh gosh, what did Gprof call it? Self and, I can't remember that other column name off the top of my head. You all have been looking at it recently. Hopefully you remember what I'm talking about. But if we're doing exclusive measurements, I'm only looking at the code that is directly in the function itself that I'm talking about. I'm not including any time from subfunctions that get called. Whereas inclusive is going to track not just how much time I've spent in that function itself, but also how much time is in the subfunctions as well. I think the next slide here has a little illustration of that. Yeah. So if we call this function, the exclusive time knows not to include this bar function call as part of the recorded time. It's only going to include the actual instructions that are executed as part of the function, not any additional function calls. But inclusive time includes the whole shebang. And I know this code isn't shown here, but whatever code is included in that particular function call would be included as part of the inclusive execution time. Or I keep saying execution time, but again, it doesn't have to be time. It can be whatever metric it is that you're measuring, right? So time is just one of the more common ones that we talk about, especially in this class. All right. So that was kind of a very quick introduction to Tau. I don't feel like I need to spend a lot of time showing you screenshots because we're actually going to open it up and take a peek at it in a little bit. What I want to talk to you about next is more practical implications of using Tau, as well as I'm going to be introducing the second homework assignment today. So I know the first one isn't even due yet, but it's almost due. And we've got a whole bunch of student presentations and stuff going on next week, so today is kind of the best day for us to start chatting about homework assignment number 2. Homework assignment number 2 is going to be a matrix multiplication, but unlike homework assignment number 1, this time it's going to be parallel. So there was no parallelism in the first homework assignment. It was just kind of meant to help you get used to the tools and the terminology and the report that I'm asking you to do. I've described it as kind of a training wheels assignment, and I think that's fairly accurate. But this one is the real deal. It's a parallel matrix multiply. I'll actually show you the code. After break, we'll take a look at the code for the matrix multiplication. It's actually not doing exactly this. This is actually a repeat of a slide I think I showed you on the first or second day of class when we talked about programming paradigms. But it is doing something similar to this, where in order to get the result row in C, we're going to take A and break it up into chunks. And then we have to multiply each of those chunks by the corresponding matrix B. And so in this example, recall, this is actually an example of, actually, we talked about this, I might ask you all this question. There was a rule we talked about actually just last time. This is an example, is it on the slide? No, I don't think it's on the slide. This is an example of what rule? Does anybody remember where each thread is responsible for a certain chunk? This would be a good exam question, actually. We say, I am thread 2. That means I'm going to do rows 20 through 29. I am thread 3, so I'm going to do rows 30 through 39. That's called it's 2 words. Owner compute rule, ring a bell, hopefully? This is an example of the owner computes rule, where we take our data set, break it up into chunks, and then each thread owns that particular chunk. It is responsible for the computations of that particular chunk. What's interesting for us to talk about, at least in regards to this matrix multiplication operation, is how we break up those chunks. So this slide that I already showed you, I know I already showed it to you before, breaks it up by rows. And the owner computes portion is down here. I grab my thread ID somehow. Which thread am I? And then out of the number of rows that I have, I know this is a hard-coded magic number, boo, but the row code is a little nicer than that, I think. I figure out, which rows belong to me in particular, and the rest of the loops are basically more or less the same. I'm using my thread ID to tell me which of the original matrix I am responsible for. But let's talk about some other ways that we can actually approach this problem, because it turns out that this is pretty good. Right? Breaking it up in this way is parallel. It is going to save us some time, but it may not be the best. It may not be the best in some certain situations. One thing in particular, keep in mind that we are, in the implementation that I'm going to give you, this is called striping, where we break up those rows. You can see why it's called striping, right? A is striped. Actually, you can see on the previous slide that B was not striped. So every single thread got a copy of the entire array B. That's a lot of data, right? Potentially extra data, more than what needs to be passed to each individual thread in order to accomplish the task at hand. So why not stripe B as well, is kind of a question that is, I think, natural to ask. Can we decompose B as well? And it turns out you can, but there are some challenges. There are some problems with doing it that way. Matrix multiplication, remember, takes rows from A and multiplies them by columns of B. So if I'm only responsible for rows, 0 through 9, I really only need the columns of B from 0 through 9 to do my multiplication, correct? So we can stripe B as well, but what's the problem with this? Why does this look like it might be a bad way to split up data compared to this? Anybody have any ideas? matrix multiplication requires us to do it that way, right? But from a computing perspective, from a performance perspective, why might this not be the best way to break up our data? Yeah?
Did you say that rows tend to be stored together, so you'd be jumping through memory?
Exactly, yeah. So when we're talking about matrices, arrays in our programs, they're stored in row matrix order, which means that on memory there is no rectangle, right? It's just a stream of data. And so how does that data actually lay out? Well, it does all the first row, and then all the second row comes after that, and then all the third row comes after that. So if I'm going down the columns, think about what that means. I'm going to read that first value in the top left corner, let's say, and that's going to pull in not just that first value, but the first, well, it depends on how big your array is, right? In the ideal case, it would pull in maybe the entire first row of data. If that row is too big to fit in a single cache line, then it would only pull in a chunk of that row. But I don't need that. I need the stuff that's in the column. So then when I get ready to read the second value, it's not going to be in cache. I have to go fetch that from memory as well. And by the time I get down to the bottom of this, that first row that I pulled in may have already been booted out, right? Because it's been in cache for a little while, especially if it's a giant matrix. So that first row of data has already been in cache for a little while. It may not be there anymore. I may have that same problem over again, where I have to pull from memory for every single value. There's a simple trick, though, to work around this. We can transpose V. So transposition is simply the act of taking the columns and turning them into rows. It's literally just flipping the matrix like that to where the columns now become rows. That's extra work. That is extra work that would need to be done prior to the threads being spawned and the data being distributed. We talked about this last time, right? When we talked about speed up or actually when we talked about designing parallel programs. Sometimes parallel programs will require extra steps of work that if you were just going to do things sequentially, you wouldn't really consider or care about. Or if you don't care about performance, if you don't care about squeezing every drop of performance out of your algorithm, you may not worry about transposing B. I know for a fact, I've seen plenty of students code up, matrix multiplication just like this, going down the columns of B. That's what the traditional matrix multiplication algorithm says to do from math class, right? And we want to make sure we honor that. We don't want to do it incorrectly, but if we care about performance, we're actually going to take some extra time and think about, how is the way that this code is written going to affect my trips to memory or my trips to cache? So one thing we can do is transpose B, which, again, would take this corner and flip it up to that corner, right? So now this becomes the first row, and this becomes the second row, this becomes the third row. Now it's a lot more cache-friendly. Now we have a structure that is going to get us the same result. I have to take a little bit of extra time to rearrange the data, but it's going to get us the same computational result and hopefully require fewer trips to memory because I'm not traversing down the columns of matrix B. There's a paper that was posted on Canvas that actually crunches a whole bunch of numbers and runs this with varying sizes of matrices and shows the results of how this actually affects true matrix multiplication computation. But as it turns out, actually this isn't even necessarily the best way to do it either. So there's another approach that if you were going to be doing things on a supercomputer, for example, maybe you're working on the next LLM model, which is all matrix multiplication. That's what it is. It's all dealing with these kinds of computations. Instead of using striping, they're going to use what's called a block decomposition. So you can see from the diagram what that looks like. Each thread is not responsible for a set of rows, but really a block, where that block size is going to be chosen such that the entire block can fit in your cache. So if my lower level cache, my LL1 cache is, I don't know, 64K or whatever the case may be. That might be a little high actually for an L. Anyway, I'm going to try and choose block sizes that are going to fit that level of cache so that I can have that entire block. Actually, you probably want it to be half because you also are going to do the corresponding block for B that you need to multiply together as well. But regardless, if all of these blocks fit into cache, that's going to get us the max speed. The benefit, the performance benefit comes from the fact that with larger matrices, the row's never going to fit in cache. The entire row is never going to fit in cache. And for really large matrices, even one row might fill up the entire cache and then some. And we are talking about really large matrices in this class. So with block decomposition, we're allowing ourselves to suit the data to the architecture. That's not how most programmers think about writing their code. When's the last time you thought about memory access when you were writing a piece of code, right? Probably not very often. It's not something we generally care about. But in high-performance context, we absolutely do. Now, the downside of this, which you can maybe already see, is that if I multiply this block and this block together, that's only a partial result, right? True matrix multiplication says the first row multiplied by the first column gets me one result in C. So I can't get an entire result just from those two blocks. So there has to be an additional aggregation step on the end where the threads send all of their results to perhaps a master thread, or depending on how you want to orchestrate it, how complicated your algorithm is, we can match the threads up to the corresponding blocks. I know you have the next set of blocks, so I'm going to send my answer to you, and you can combine your answer together, and so on and so forth. There's lots of ways that this can be approached. I think the great point, though, the big takeaway here, though, is that in order to get that performance out, right, it takes work. It takes extra programming. It takes extra thought about our algorithm. The general algorithm for matrix multiplication, not hard to understand. I teach it to my intro students, right? It requires a few for loops and maybe an if statement or two. It's not complicated to understand how to actually do a matrix multiplication. But again, if we're trying to squeeze everything out, if we're trying to write a parallelized version of this program and squeeze out every possible drop of performance that we can, the naive algorithm isn't going to cut it. We need to think about our architecture, we need to think about communication, we need to think about caching and all of those things, how much memory we have. All of those are a factor. And those are things that, again, the typical programmer is really not thinking about, not taking into account for their average program. This is another paper. It's actually, no, it is the same paper. I was trying to remember if it was the same paper or a different paper. I think it is the same paper as the one referenced on the previous slide. That work actually done right here at WashU, by the way, presented at a conference you can see back in 2020. But this has become widely accepted and is now the way that matrix multiplication is performed in high-performance contexts. And actually, this is an option for you to do on the upcoming homework assignment to see if you can implement this and compare that to the striping implementation, which is the version that I've given to you to start with. So if you want to do some programming, play around with that. And I'll just note as well, taking a stab at this and I don't want to say failing, but like not getting improvements, that's still worth writing about to me, right? Especially if you can figure out why. Especially if you can tell me why. If you take a stab at rewriting the code to do block decomposition, and you're like, I couldn't get it to work. It does the multiplication right, but it's slower. That's okay. Analyze it. Tell me why. That's still a worthy use of your time. That's still a worthy thing to write about. That's still learning, right? Learning what doesn't work is still useful information. So I don't want to scare any of you off of this if it's something you're interested in. You don't have to get it exactly right. If you still do a good job of analyzing it, collecting the data, and writing it up, that's still going to be A-okay with me. All right. We're going to take a look at these a little bit later when we get to the time where we actually are running Tau and analyzing some actual code using the tool. But I wanted to just kind of briefly go over the pthread structure again in a little bit more detail this time, since we're going to be using pthreads directly on the upcoming homework assignment. This is another example that I showed you, I believe, on the first day of class or so, maybe the second day of class. And so the big things to take away here are this pthread create function and then pthread join, where pthread create, as its name implies, does the creation of the thread, and this is going to be a blocking thread. So if the thread is not done, or the blocking call, so if the thread is not done yet, we're just chilling here until the thread finishes whatever it is. In this particular case, probably not waiting too long, because as you can see, the function that we've assigned to be executed to the thread is pretty trivial. But on our matrix multiplication example that I'll show you, that's not going to be as much of the case. And then this is another example that I showed you, but again, trying to make sure everybody's clear on how to use pthreads, especially if you're planning on maybe doing some code modification, which I want to encourage you to do. So here's the creation and the join calls here. This time we're passing arguments. This is the fun void pointer thing that I talked about a week or so ago. But on the next slide, yeah, we have some more details as to exactly what's going on. I know that's an opinion, but I feel like it's a pretty reasonable opinion to have, that passing parameters to threads is a little odd. You may not agree with me, that's okay. But the void pointer business is a little bit weird. It's old. These have been around for a long time, so I think that has a lot to do with it. C didn't have a lot of the capabilities that the modern language of C and C++ that we know has. So void pointers it is. We have to declare a structure with our arguments and pass it in. So especially if we have lots of arguments, right? Because you'll notice that in this simple case, if I just have one argument that is a string, this character pointer here, right? Then yeah, I can just cast it to a void pointer and then cast it back to the appropriate type. But what if I have lots of arguments? What if I have more than one argument to my function? It doesn't give me the ability to add more over here. So we have to declare a structure. We have to declare a struct with an entry for each one of our arguments, right? Then we have to cast that whole struct to a void. We have to fill that struct with the actual arguments. We have to cast it to a void pointer. And then when we get into the function itself, we have to cast it back to the struct and extract all of the arguments out of it. That is how it's done on the homework assignment. So I'll show you an example of that when we get our hands dirty after break. But we are going to look at these two just to do some simple. We'll use these just to check and make sure that everybody can run Tau and everything is the very basics are working at least. And then we'll take a look at some more complicated code after that. The way assignment 2 works. There's a master thread that is kind of responsible for setting everything up. And it also does some checks at the end. So it actually verifies the code, the results rather, to make sure that they're correct as well. One thing to keep in mind on the assignment is that this master thread is actually not doing any of the matrix multiplication itself. So that means you can actually have one more thread than you think for maximum parallelization. In other words, if you're running on an 8-core machine, you would expect that 8 threads would probably be max saturation for that CPU. But because the master thread is idle during the actual matrix multiplication phase, I can actually run it with 9 threads, and there will only ever be 8 threads running at one point in time, because that master thread is just sitting there waiting. In the meantime, it's idle. So you can go one thread higher than you might suspect for the number of cores. Yeah, it says that here. Core in the opposite direction. Core count can be one fewer than the max thread count. Although, that being said, I think it's also interesting to push it. If I have 8 cores, what if I run 16 threads or 24 threads or 32 threads? See how that performs as well. You might be surprised. You might think that oversaturating it would start tanking the performance, and you're right. It will, but will it tank it as fast as you suspect? Maybe not. Maybe not. So definitely make sure to explore, if you choose that option on the homework assignment, that I'll show you in a little bit, make sure you explore using more threads than you have cores as well. I think that's interesting and worth talking about. All right, creating threads. The last time I talked to you about this, I tried to do it from memory, which was a mistake. I can't remember all this stuff, nor should you need to remember all this stuff, right? That's what documentation is for. That's what we're trained as programmers to do, is to look things up. So here is the documentation on creating threads so that I don't botch it this time. We're actually passing in the thread pointer as the first argument. These are going to be some attributes. We typically don't use those for our threads. If you want to look up the documentation and see what those attributes are, please be my guest. But I think for the most part, we just don't use them. Instead, it's a null. This is the routine that the thread's going to be executing. So it has to be a function that is visible, that is within scope, and then as we talked about the arguments, which I'm going to show you in a little bit. There's a few different ways we can terminate our threads, have them exit. So if we don't do anything, if we just say, hey, go do this function foo, and it'll run that function foo, and when it gets to the end of the function, it'll say, okay, I'm done, and then the thread will just go poof. Right, and it'll exit out. But you can also call pthread exit, or if the master thread calls pthread cancel, which I believe takes in an argument to the thread pointer, even though it's not listed on the slide. Again, double check the documentation just to be sure. Then it'll cancel the thread for you. This last one seems a little silly, but it can happen. If main finishes without, calling pthread exit or anything, why would main finish if the other threads are still running? Doesn't that seem kind of silly? Why would the main thread be done before the threads are done? Well, that's where the pthread join function comes in, right? If you never call that join function, you're never going to get the information back from that thread. Maybe you don't need it. Maybe you don't need maybe the thread doesn't need to pass information back to the master thread. In our program, it does. In our program, it absolutely does. So we need to have that call to join in order to get that thread to finish properly and return its information back to the main thread. But if you find yourself in a case where you don't join the threads back, either because you don't need to or you just plain forgot, then if the main thread finishes first, all your other threads are going to die at the same time. All right, back to tau. I know we took a little detour there, but we're back to tau. If you want to use tau on your personal machine, I don't recommend it. Let's be honest. It's kind of a hassle. It's kind of a pain to get it set up. I have had students do it before, so if you are gung-ho on having this tool on your computer, some people just wanted to have it. They thought they might use it for other stuff later on, and that's great. I'm not going to discourage you from doing that. If you're just trying to get the homework assignment done and that's your goal, I don't know if I would even recommend it as being worth the time. It takes some effort. It takes some work. You have to go download a couple of different things, the tau code itself, as well as this PDT library, which is for, oh gosh, what is that acronym for? I have to look that one up. I don't remember off the top of my head. But you have to install both of those things on your machine, which is easy for me to say, and anybody who's tried to install stuff on Linux knows not always as easy to actually do, depending on your familiarity with installing stuff via command line and everything. So I don't want to, I guess I kind of am discouraging you from doing it, but if you really want to do it, you can. It's freely available. You don't have to pay any money or anything. You can go download it and install it on your machine. It has been installed on the Linux lab machines for us, so you don't have to do this. It's not a necessity. But just in case you are interested, I wanted to point out that those resources are available. And this is more for, again, if you want to install it on your machine. This is not something that you are going to have to do to complete the homework assignment if you don't want to. But you have to configure Tau first, which means you have to tell it things like, where is this PDT library that it needs to run? What kinds of programs am I hoping to compile and analyze with Tau? So you can see the options here for MPI and OpenMP, pthreads, right? So you have to pass all that information in via configuration. I linked the documentation there in case you're interested, although if you're installing it yourself, you're going to be reading that documentation for some time, I promise you. There's a lot of little things and so many knobs and so many things that you can adjust and tweak with this tool. But we don't have to do that because we have the Linux lab machines. Now, like with perf, gprof worked out of the box because that's a pretty low stakes tool. Perf, because it accesses some stuff from the kernel, they make us use that srun command, right, to use perf because it requires some elevated permissions that IT doesn't normally give, but they're trusting us. And Tau is the same way. So the unwritten step that is before this is you still have to do the srun command before you try to load Tau in. But once you run that srun command, and I'm going to show you all this after our break too, we're all going to get a chance to go through and try this out. Once you have run your srun command to start the job, you can simply run module add tau-cpu. IT has set it all up for us, so we have to run this module add. This loads a whole bunch of stuff into our path to let it know where tau is. However, it doesn't load everything. It doesn't set up all of the paths. There's still a little bit of manual work we have to do. We have to set this environment variable for the tau makefile. This is literally just a copy-paste thing. The downs, and this one, well, so this only applies for homework assignment 2. We are not going to be using this PDT library for homework assignment 2, so this one is another one that I recommend you use for homework assignment 2. The downside is that these aren't persistent, right? So if you fire up a Linux lab machine, you get Tau set up, you run those 2 export statements. The next time if you come back the next day and you fire up a new instance of the Linux lab machines, you still got to run those export statements again. That's kind of a pain in the butt. There's 2 ways around that. Obviously, you could write a little script, or if you're familiar with Linux command line tools, you can add those to your bash RC. I'd be happy to help out with either of those particular things if you need some assistance with that, getting things set up. Once you've got Tau added and you've got the proper environment variable set, then when you compile your program, you can actually do it through the Tau version of the compiler, which, as I said, is really just GCC, but with a whole bunch of Tau stuff added onto it. So GCC is in there somewhere, but Tau is also doing its own thing. So you're not going to compile it the same way. You're going to compile it using Tau's compiler, and then you just run the program normally. If you've compiled it using the Tau compiler, you don't have to run it any special way. You just run it normally. And once you run the program, it will spit out a file that is called profile with some numbers after it. Is that on my... Yeah, here it is. It'll look like this. Profile with some numbers after it, where I'm not quite sure exactly what the first 2 numbers represent, but the last number, I believe, does in fact represent the number of threads that were used for this particular execution of the program. And it won't delete those files, so if you run it multiple times, it will create additional files. It won't erase your old data. It'll actually keep it all there. This is how you can actually run tau on a compiled binary. So the homework assignment that I provided to you comes with a makefile. It's a pretty simple one. It's not complicated, but if you want to do it this way and experiment, I think this would be a perfectly viable avenue of exploration for the homework assignment, for one of the questions on there. I'll talk about that a little later. But you could compile it using the makefile and then have tau augment the binary. Now, in order to do that, you have to use this tau exec executable to run your program. And then there's some extra options that you need to make sure that you are including, because when you run it this way, tau assumes you're using MPI by default, which we are not. We're using pthreads on this assignment. So we have to tell it to use pthreads, and then this looks like we're telling it to be serial, but that's just saying we're going to start with one master thread and then use some more pthreads from there. So make sure to include these flags if you actually want to try using the binary one. I kind of don't recommend it so much, but with the event-based sampling flags on there, that can be an interesting way to see the execution of your program. So it's available for you should you choose to go that route. All right. As far as how to access the visualization, so once you compile your program and you run it, if you want to see the results on the command line, you can use this pprof tool. I'm not gonna show you that one. You're welcome to play around with it if you want. It looks kind of gprof-like, right? Similar. It does not give you all the bells and whistles, though. Clearly, on the command line, you don't have ways to get fancy plots and things like that, like I was showing you on previous slides. So I'm going to show you how to do the visualization stuff, because that's really the fancy stuff that I want you to get access to. And so that visualization tool is called Paraprof, and you can just run it directly, as long as you're in the directory where those profile files are. You can just call Paraprof, and it will automatically locate any profile files that have been generated and load up the data from those profile files. And it'll show you a window like this. And so the user interface, again, you can kind of tell that the people who made this are people who are down in the weeds. The UI is not the greatest. It takes some getting used to. That's what the documentation is for. I have definitely struggled to get Tau to show me what I wanted to show me sometimes, but we'll get some practice doing that here in just a little bit. Yeah, more visualizations. I kind of already showed you this one, so. And so then with the Linux desktop, this is what we're going to do actually after break here in just a little bit. So if you want to use Tau using the Linux desktop, which is how I actually would encourage you to do it, the way that it's going to work, and again I'll show you all this after the break, but just so you have it in writing as well. It's kind of clumsy. It's kind of awkward. You got to fire up your instance. Again, you want a visual one so you can get access to those visualizations. So you're going to want to do it through the web browser, right? Fire up an instance in the tab through the web browser. Once you get in, you do need to fire up a terminal and SSH into shell still from the Linux instance. I botched it last time, but I figured out what I did wrong, so I'm not going to botch it today, I promise you. Well, I shouldn't make that promise. Things can always happen, right? But I did figure out what I did wrong last time. So if I make a mistake, it at least won't be the same mistake that I made last time. It'll be a different one. So, so yeah, you have to SSH in. You have to use srun. I can definitively state that you do not need these $signs. Don't put the $signs in. That was one of the possible mistakes that I was making last time. You don't need the $signs. Just put a number here. No bigger than 8, please. Technically, you can request more than 8 cores, but remember that there are other people that need to use these machines as well. If you really want to use more than 8 cores, I would say like this weekend might be a good time to try and do that. Like if you really wanted to try and blast some, lots of threads at a big machine. Homework 1 is due on Friday. There'll probably be very few people trying to access these machines over the weekend, I would say. So if you really want to go more than 8 cores. Do it early. If you're doing it towards the end, closer to the due date, please do not, because I would imagine that there will be several other people trying to work on the assignment during that time as well. There are a limited number of cores, so please keep it to 8. And if you're unsure, just keep it to 8. Job name, again, no $ necessary. I usually just use my whistle key, my name, something like that, so that I know that it's mine. And then I already kind of went through all these steps. We're going to do all this. We're going to get some hands-on experience doing all this stuff after break, which I think is going to be right about now. But before that, does anybody have questions? Any questions I can answer? That we've covered so far? Hopefully, if you do have questions, which I'm not seeing, we'll get them answered once we get our hands dirty with Tao after break. But let's go ahead and take our 10 minutes. I think that'll bring us back at around 6:45, let's call it. Stretch your legs, hit the bathroom. Around 6:45, please, I see it looks like most of you brought your laptops and stuff today, which is great. Hopefully, I want you all to be running Tao before you leave here today. And we're going to take a look at the write-up for the homework assignment too, before you all leave here today as well. Cool. See you after break. I'm going to check the weather too. It looks kind of nasty out there, doesn't it? All right. I did check the weather, and it looks like it's gonna hold off until around 8 o'clock or so, which I know is right when class is supposed to end. I think we probably will be done a little bit before 8. But I want to repeat that if you're worried about, I don't know how far y'all have to drive to get home and stuff, right? So if you're worried about it, please don't worry about upsetting me. If you want to take off early, make sure you get home before the storm. Not going to be upset about it at all. If things go well, I think we'll be done by 7:30, 7:45, probably somewhere in that time frame anyhow. But just wanted to kind of give you all an update about that. It doesn't look like it looks threatening out there, but it's not doing anything quite yet at the moment. And I really would like to get y'all set up with Tau for homework assignment 2 before we leave here today. So let's start off by just taking a quick peek at homework 2. You can see that, like the last one, it's kind of a choose your own adventure situation. I've given you 12 prompts here, some of which you might recognize from the last one. If you want to pick the similar types of questions as you did on the previous assignment, I don't have a problem with that because this is a parallel one now, so it is going to change things quite a bit compared to how it happened last time around. So I think there's enough of a difference there that even if you do pick similar questions, it's going to be substantially different enough to require a little bit more thought, a little bit more effort into it. I do want to point out these two at the bottom. These are the ones that I was talking about that are going to require a little bit of extra coding. Some of these other ones might require some minor changes to the code, but probably not like huge changes. These bottom two, though, will require some more substantial changes to the code if you're interested in doing that. Transposing a matrix is not hard to implement, so that one I think is probably the easier one of the two if you're looking at doing some programming on this particular assignment. The blocking one can be a bit tricky. So again, don't want to discourage you from doing it, but to help you out with that, I mean, again, this paper has been posted on the Canvas page. If you're going to do either one of those, 11 or 12, I would highly, highly, highly recommend reading that paper first. There's some good insight into how those operations would need to be implemented, how they're going to work. One other thing I want to point out, last time I didn't do this. Last time I gave you, complete free will to do whichever ones you want. This time I am going to make everybody do the first one. You have to do question number 1, which is about Tau. I spent all this time talking about Tau. It is the gold standard, like I said. If you're doing anything in HPC, you're going to be using Tau. So I'm forcing you all to do Tau on this one. You have to answer question number 1. Everybody has to do question number 1 for this next homework assignment. But for your other questions, you once again can pick whichever ones you want to. It's completely at your discretion. So with that out of the way, let's go ahead and get everybody hopefully up and running with Tau. I'm going to be using the Linux lab, the visual one, right? So using Tau, I think, kind of essentially requires it because you can't get the windows and all of the bells and whistles through SSH alone. So go ahead and navigate to the Linux lab. I think there's a link on Canvas, or you can just Google WashU Linux lab, and I think that also pulls it up, right? So make sure you get to the Linux lab. Well, there's a few different links, but they'll get you there eventually. Yeah. Go ahead and click on the My Interactive Sessions tab at the top. Here's the one that I was playing around with earlier today just to make sure everything was working properly, but I don't need that anymore. I'm going to go ahead and make a new academic Linux desktop. It's this first option right up here at the top. Let's go ahead and click on those. I doubt we'll need it for longer than an hour. I mean, we only have about an hour left, so I doubt we'll need it for longer than an hour. And for this particular purpose, we probably don't need more than 1 core either. So I'm going to keep those at just their defaults and hit the launch button. This takes a moment to spin up. I actually looked it up too over the break and figured out that there are 128 cores total available. So I was curious about that the other day. Although that being said, the documentation I looked at was also clearly out of date. So I don't know if it was entirely up to date. Now, let's say there are at least 128 cores. I doubt they took any away. If anything, they probably hopefully have added some since then. But just so you know, there's 128 cores on our cluster total. All right. Once it's launched and running, you can see mine says it's running up here. We're going to click this button to open up the tab. Okay, and actually the first thing that I want to do is probably open up the web browser and go to Canvas. I was going to run through those simple pthread examples that I showed you on the slides, but I think for the sake of time and relevance, I'm just going to skip right to the homework 2 assignment and go through that code with you and run that code through Tau with you. So first I need to get to Canvas. This is a little bit clunky. I'm not going to deny that there's some hoop jumping that needs to happen here to access all of this and get it set up properly. But that's why I think it's important we do it all now so that everybody has at least done it once. Yep. Never. Okay. So I'm going to go to the Canvas page for our class and just go right to the homework 2 assignment and download the tar file for that assignment. So this link right here is what I'm going to be downloading onto this virtual machine, homework2.tar. There it goes. It should now be in my downloads folder, but it's compressed, right? So we need to, oh, here's all the runs that I did from earlier today. Well, let me get rid of those real quick, just so that I'm not confusing all of these things here. All right. So yeah, we need to get this extracted real quick. Boop. You can do that via command line as well, but potato. There's only 2 files in here. There's a make file. It's a very simple make file, I want to say. Yeah, not a whole lot going on in this make file. Pretty straightforward, but I won't actually be using this make file today. You can. I gave you the instructions on how you can use Tau to augment the binary. So if you want to try that out as part of your explorations, you're welcome to do so. But I'm going to do it, I guess, a bit more of a standard approach. Maybe before we do that, though, let's take a look at this code real quick. Because this is a bit of a beefier program, I think, than the last one that you did for the first homework assignment. We've got our 3... Can I zoom in on this at all so you can see a little better? Oh man, it loaded up Emacs by default, and I'm unhappy about that. What else do we have on here? Yeah, just give me a generic text editor, please. Is it going to open Emacs again? Oh, it's not going to open anything. Okay. Okay. Well, now I don't have syntax highlighting, though. That's all right, fine. I'll suck it up. Well, okay. Sorry about that. I don't need to be futzing around with text editors right now. We've got our matrices defined up here at the top, and as well as our number of dimensions. This max thread thing is kind of arbitrary, not strictly necessary. You can, of course, go above 20 threads if you really want to, although you'll have to change that constant because it does check. It does check against that max thread constant later on in the code. But here is the thing that I really wanted to point out to you. This is a struct that has an ID number, total number of processes as well as the dimensions, and then pointers to each of the three arrays that are going to be multiplied together. So we're defining the structure because later on down in the code, here's our worker thread. So this is the function that has been written to do the actual multiplication, and it accesses the three matrices here, you can see, right? But when we spawn the threads using pthread create, which is right here, you can see that, okay, we have to set all of these values into that structure first. And not only that, we have to make one of these structures for each thread, because each thread is going to be getting a different set of arguments. Well, some of them are the same. The pointers to the arrays are the same, but the other arguments are going to be different. So for each thread, we have to set the values of the struct, and then when we call pthread create, we're actually passing in that entire structure. Yeah, it is a little bit clunky. It is a little bit complicated, but notice that the actual matrix multiplication part is this function call here, aptly named mm for matrix multiplication, which is, where is that guy? Oh, it's right up above. I was going the wrong direction. Here's what's doing the actual matrix multiplication. You can see it is a triple loop, just as you would probably expect for matrix multiplication. This is not optimized. I think it even says right up the top, unoptimized, right? So this is a pretty naive approach, pretty non-optimized, at least for parallel execution approach to this matrix multiplication. That's intentional. I wanted to give you some room for improvement, right? To make your own improvements to this code. But I also want to make sure you understand all of this thread business. Be careful when you are modifying stuff, right? It's very easy to break things. So just be aware of, I know there's a lot of arguments here, but it's important to understand. I don't think these attributes are actually being set to anything. We can see them, well, are they though? Yeah, there's a function for that. Where's that guy? Or is that a library function? That's a library function, I bet, because it starts with pthread. So I don't know what those attributes are being, probably just defaults would be my guess. Have to check the documentation on that one. But yeah, and then the master thread, once all the threads spawn, the master thread just sits here and waits. So this loop here is quite literally just going to sit here and wait until all of the worker threads are done. So the master thread is not doing any of the work, not doing any of the multiplication. So there is kind of an extra thread here, which is a potential optimization you could try and make as well, I suppose, while you're at it. But what the master thread does do, there's an option to print, which you can see is commented out. I would leave that commented out unless you're trying to debug, because printing takes a crap load of time, right? So printing the matrix is going to slow you down big time. So don't print unless you are updating the code and need to debug and make sure it's still working properly. But what it does do is it actually checks the matrix as well down here. So it's doing kind of a naive comparison as well. Obviously, we care more about the parallel section of the code. If I would even argue that you could potentially take this check out, again, unless you're debugging or something like that. It's not as essential as what the worker threads are doing in parallel in terms of the performance aspect of this code. But you have some wiggle room there. I'll let you all make your own decisions as far as that goes. What I want to do is get this up and running and make sure that we can all use tau properly. So in order to do that, I need to get rid of this window for now. And I'm going to fire up a terminal. So we do need to SSH into shell, which somebody mentioned this to me on Monday as well. It was actually redirecting. Is it still redirecting to the secondary one?
Yes.
Yeah.
Yes.
Shell 2. I believe you. I'm just gonna make it tell me that. So yeah, I don't. They must be doing some maintenance on shell 0 or whatever. I don't know. They must be doing something because it's been redirecting, but that's okay. It did this to me earlier today, I think, as well, and still works just fine. So you do need to SSH into shell2.engineer.woostel.edu. Oh, I forgot my login up here. That's an important part. Well, actually, it would have worked out okay because my username is the same, but still, I have to do it this way. Great, awesome. And then here comes the fun part where we have to do the srun command. We have to say srun, and then I left the slides open because I never remember all of the different arguments and stuff we need to do. -p Linux lab, -c cores. So if you want to run a machine with lots of cores, the VM I think should always be 1. If you want to run a machine with lots of cores, this command is where you would need to specify a number bigger than 1 if that's something that you're interested in doing. So it was -p, I think, Linux lab, -c, and then you can put 8 here. I'll try it with 8. Well, maybe I'll go to 4 just in case, because if you all are also doing 8, I don't want to overload the system if everybody's taking 8 cores. -j job name, so -j, and then dshook, or your name there. Doesn't have to, probably shouldn't be my name, right? That would be a little confusing / misleading. And then we have this fun -a business, and all right, cool, almost there. -a engineer class any --pty/bin/bash. I think this is right. Fingers crossed I didn't make any mistakes, but could happen. All right, cool. I think it worked this time. Yeah, awesome. Everybody, let me pause here. Did I leave anybody behind? Everybody okay? So far, so good. We haven't actually done anything that we kind of haven't already done with the previous assignment, but we're about to, because the next thing that we have to do is we have to run those export statements. And again, if you want to stick them into your bash RC so that you don't have to keep doing this every single time, that is actually a pretty good idea. I was tempted to do that myself, and then I was like, well, I want to show everybody else how to do this. So I actually haven't updated my bash RC yet, but I can show you how to do that real quick. Since I'm here, can I paste? No, you're not gonna. Oh well. Exports. Oh man, this was much easier at home when I had 2 monitors. Tau makefile equals. The nice thing is that we can do. This is an actual path that exists. So project engineering. We can use tab to autocomplete. Hopefully you all are familiar with that. On the command line, and then tau. Yeah. Oh yeah, there you can see all the different versions of tau, right? So on future assignments, we'll probably be using the corresponding versions of tau. But for the pthreads one, it's just going to be that one. x86, 64, lib, makefile. All right, fun stuff. All right, here's the command. I'll leave it up on the screen in case you are trying to do this one yourself. Give you just a moment. So we're going to run that command. And then we have to run a second one because we are not using this PDT library on this particular homework assignment. I believe we will have to use it when we do OpenMP and MPI. So we have to run this one as well. Export tau options. and then it was dash opt compt install. I think I got my capitalization wrong, didn't I? Yeah, the first one was supposed to be lowercase. Ah. Is that right? Nope. Almost. That's right. Okay. So there's the second export command. And if that annoyed you as much as I did, here, for those who are less familiar with how to use the command line, there's a file called .bashrc, and you can actually put those export statements in this bashrc file. I used Vim to open it up because I'm a Vim guy, but it's just a file, so you can go track it down in the File Explorer too if you want to. It should be in your home directory. Wow, there's a lot of stuff in here. It should just be in your home directory, although it is a hidden file, so unless you have the hidden files option shown here, you won't be able to see it. But once you turn hidden files on, and if it doesn't exist, mine exists because I've played around with it before, but if you don't have a bashrc file, make one. Just go ahead and make one. You can open it up and then copy paste those export files just right into this .bashrc file, and then you will never have to type them again, although it won't actually take until you spin up a new instance, right? So just kind of keep that in mind. And if you have trouble doing that, I'd be more than happy to help you out with it, make sure that everything is set up properly. Okay, so we've got our two export statements. Our next command is to do module add tau CPU. Oh, that auto-completes too. That's nice. I like that. Yeah, you can see the other ones for OMP and MPI that we'll be using later on. But for today, we're going to be using module add tau CPU. Boop. And now, finally, we are ready to compile our code. So my code, I think, is in the downloads directory. So I'm going to cd into downloads, cd into the homework 2 directory. There's my C code right there. You can, as I mentioned, use the make file if you want to and compile it using make, but I'm going to do it using the tau compiler. So, and you can see there's a whole bunch of compilers available. This is actually kind of an interesting thing to show, right? Tau is trying to do it all. Tau is trying to do any language that people could care about. So you see Python, you see Java. The one that we're after is tau CC for plain C, and then there's CXX for C++ codes. But yeah, we're going to be using the tau CC .sh -o. Oh, what do I want to call it? Matrix? I don't care. And then pass in the code itself. Something like this should do the trick. Okay. Uh-oh. What do you mean my export statement didn't work? Oh, I spelled it wrong. Haha. I told you I'd make a different mistake this time. That's an easy one, though. All right. Fix my typo. Try this command again. There we go. That looks a lot better. Well, it looks like compiler junk, but that's better than an error, so happy with that. Everybody okay? Anybody have any problems? Not seeing any problems, so that's good. If we do an ls, we should be able to see that our code was successfully compiled into the binary, and now we just run it like normal. Be careful because you actually have to pass in an argument. You have to tell it how many threads you want. So I'm on a 4-core machine. I could pick 4, or I could pick 8 if I wanted to. There's, I can definitely use more threads than I want to, or more threads than I have cores if I want to. And there we go. Boom. I ran mine with 8 threads. If you forget to tell it how many threads, I believe it's gonna give you an error. Yeah, it'll tell you to provide it with an argument, but the first time I ran it, it seems like it was successful. So if I take a look now, you'll see that, oh, wow. So actually, what we're looking at here is one for each of the threads that was created. Although, why is there 9 then? 0 through 8? I'm a little confused. Because I did say, is that the number of worker threads? And then the 9th would be the... I don't think... let me look at the code real quick and see. Let me double check the code on that one. I thought I just... Oh, here it is, yeah. So here is n. So it is looping n times, where n is the argument. Yeah, I think actually it did spin up. So it's 9 threads total, because the master thread is not included as part of n. So there would be 9 threads total. The master thread, which is presumably thread 0. Well, no, actually, it's saying, well, yeah. Anyway, okay. So that's all just to execute the code. Now, in order to actually view the results, we need to use the paraprof tool. And get this out of my way. We are SSH'd in the shell right now. So if you try to do paraprof, it wouldn't work. I think I can just show you that, right? It'll say, I can't, yeah. I have no window. I can't make a window because I'm SSH'd in the shell right now. So here comes the extra hoops. More hoops to jump through. I'm going to open up a second terminal. So this one is not logged into shell. This one is just accessing the virtual machine. The good news is that we don't need to do a whole lot in this one. We just need to navigate to where our results are, which is in the homework 2 directory. So here we are. I can see everything. And now we have to do the module add command. But the good news is I don't have to do those export statements again. I don't have to do the srun command again, right? From here, I can just run paraprof. And voila, here we are. Cow is up and running. Before I start clicking around and exploring here, though, just want to pause and check in with y'all. Did we get this far? Hopefully. No? Having problems? Where did I lose you? CPU. Oh. Yeah. No, it's okay. I'm making typos too, man. And I couldn't figure out how to blow the font up, so that's probably another contributing factor. Anybody else having problems? Especially if they're easy problems. Those are the best. Yeah.
I had the same Java errors on the last problems, but I didn't log into
The same Java errors? Like it's not able to show a window?
Yeah.
You are SSH. It says at the top. You're SSH'd in. So you don't need to SSH in on this. I didn't SSH in on the second one.
Oh, you're just on the local.
I'm just on the local.
Okay.
So exit out of SSH and then
open up a. Okay, I got you.
or just kill that terminal and start fresh. Yeah, might be a quicker way to do it. Yeah.
Could you scroll back like the commands you ran after
Which terminal? The first one. Yeah, 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 yeah.
And the file.
Yep, yep. Happy to. The compilation is right here. That's the compilation command I ran.
Saying how
See,
CC is not found.
oh, did you do the module add? Well, I saw you do the module add. Tau, T-A-U. No, you're good.
It's 7 o'clock, right?
I understand. I understand completely. Yeah, yeah. You want to see how to run the code, run the command? The 8 is how many threads, how many worker threads. Yep, yep. And then once you run the program, it spits out all of these profile files. And that's when I switched over to the second to do the visualization part. This is all recorded too, so if you need to refresh your memory, it's all available to you. I'll make sure this gets posted on Canvas. Anybody else? Anybody else? That's exactly what I wanted to help with and make sure is solve problems like this. So please don't hesitate if you're stuck running into issues.
I have results, but I think they look different than yours, and I think that's probably because I just like have different number of cores or something.
Yeah, if you don't have the same number of cores, I wouldn't expect them to look the same. Even if you do have the same number of cores, I wouldn't expect them to necessarily look the same. But they look reasonable to me, right? It doesn't look outrageous. Yeah, if you have more cores than I do or fewer cores than I do, I would expect you to get different results. So that's not necessarily a bad thing. Mine do look like they took a lot longer. So I kind of did that on purpose though. I only had 4 cores and I was running 8 threads. So I flooded my CPU.
I logged in and logged out a couple times, and at some points I had 1, at other points I had 8.
Oh,
Not totally sure which one it ran on.
based on your results, it looks like probably 8, I would say. But yeah. So what are we looking at here? This is called the Paraprof Manager, where it shows you basically a whole bunch of stats you can see over here, like the CPU you're running on and all the different specs and stuff, which, of course, that context is important, but this isn't really the data stuff. This isn't really the fun stuff that we care about the most. This window over here, this is showing us the actual results. So we see that I've got all my threads here, and then it's showing how much time each thread was spent doing work. And so the master thread, you can see, actually was pretty tiny, relatively, whereas these other threads spent a lot more time. And you can see the variability almost certainly is because of the fact that I had more threads than cores, and some of them had to be scheduled off and then scheduled back on. That's gonna require them to. That's why they. There's some variance in there as well. And so if you want to get to some of the more fancy features, right, that can be a little bit tricky to navigate, but you can. How do I want to get there? Oh yeah, let's take a look at this legend real quick first to see what these colors actually represent. So you can see that it even lists colors for tau itself. So it's telling us, hey, here's how much time each of these threads spent just reporting back to me, right? But of course, the vast majority of the time, the big chunk of time is spent in that NN function, which is doing the number crunching. That's what's actually doing the multiplication. That's what I would expect. You can see that only the thread 0 is running main because all these other threads aren't running main at all, right? They're being spawned off of that. So I don't see any of this green color showing up other than on thread 0, which is my master thread. So yeah, lots of good info here. If you want to, you can click on the 3D visualization, which will, oh, fancy, right? As promised, gives you a breakdown. It says MPI, which is really funny because we did not use MPI. I don't know why they've somehow decided that we did. Um, but, and actually, this isn't really showing us the useful. What is this showing? It's hard to see. This is almost, oh my gosh, this kind of hurts my brain. No, it is showing. These are the function names over here, MM, main, worker. I know it's hard to see. It's hard for me to see, and I'm staring right at it. So these plots can be a little finicky, but you can see the ridges from the matrix multiplication dominating this execution time here, right? So that's kind of an interesting thing to see. But if you don't want to deal with the fancy plots, or if you want to drill down into more detail, you can actually right-click on one of these threads and drill down into an individual thread. So I can actually take a look at, just the data for one of the threads. And oh yeah, here we can clearly see that the matrix multiplication was the bulk of the time. The other functions, not so much. Or for the main thread, what's it spending its time doing? It's spending its time, wow, it actually spent more time reporting back to tau than it did actually running the code that it was supposed to run. That's kind of crazy. Um, you can see that it shows exclusive by default, but if you want inclusive times, there's an option to switch that. Where was that? Here it is. So you can switch it to inclusive, which, did that even change anything when I switched it? I can't tell. Oh, it did change, yeah, the numbers changed a little bit. The graph was hard to see, but the numbers did change a little bit. So yeah, drilling down onto each one of these threads, especially if you see a thread that stands out in particular, like some of these do seem to stand out, right? Now, what it's not showing me, what's a little bit hard to see, is like, why is this thread taking longer? Clearly, I can see that it was in the matrix multiply program, but I'm imagining that it's because it got preempted by the operating system, because there's too many threads for it to run all of them at once. That I can't quite determine, right? Just from looking at the execution time. So what I don't have available is the ability to show, other counters on here. I think you need to set your tau options. Like if you want to record cache misses or preempts by the operating system, something like that. Those are options that you're gonna have to dig down and find. They're there. It can do it. I promise you, it can. But I'm totally gonna leave some of this stuff up to you to dig into the documentation and figure out how to do those things. And that's one of them. But yeah, the call graph is available, although not very interesting for this particular program because there's just not a lot of functions being called really. But and some of those it looks like maybe not quite accurate. If you look at the call graph, like clearly the main thread is doing more than just main, but it seems like maybe some of those other functions were optimized away during compilation perhaps because they aren't showing up on the call graph. That's always the risk of using compiler optimization. You lose some of that information that way. Trying to think if there's any other super important stuff that I should show. I mean, I think I covered all the highlights. I showed basically the same stuff as, yeah, all kinds of fun things. Wow. That is not a very useful histogram, I would say, but it is a histogram. What do these bars? Threads. Wait, what? Oh, I see. This is showing how many threads fell in these buckets. So I had 3 threads in this bucket. 1 thread fell in this bucket. 2 threads fell in this bucket. 2 threads fell in this bucket. That's what it's showing me. And that matches with what I'm seeing on this bar chart as well. I've got 3 that took a little longer, 3 that took kind of in the middle, and then a couple that were fast. So my goal today was not to show you that everything that Tau can do. I don't have enough time to do that, even if I wanted to sit here and show you everything that Tau, and it wouldn't be useful for you anyway. That's what the documentation's for. My goal was just to kind of show you some of the basics and make sure that everything was up and running for everyone. Does anybody have any questions? Is anybody still struggling with Tau? Anybody need help at all? If not, it might be a good time to. It looks clear out there right now. I don't know if it's still going to storm on us, but I'm done. I will stick around though. If you have questions, if you want to work on the homework assignment, either homework 1 or homework 2, if you want to ask questions about homeworks, presentations, anything at all, I won't leave until all of you are gone. But that's all I had on the agenda for today. So thanks everyone, and I will see you on Monday. And please let me know if you're still struggling to get Tau up and running.